Problem statement. A company claims that their fries have an average weight of 54 gram per pack. To test it, you buy 25 random packs and you weigh them. And these are your corresponding weights. So the total of these 25 sample, it comes out to be 1250 gram. So the average weight of the single pack is 1250 divided by 25 and the answer is 50. Well, they seem lighter than the claim. Your claim is 54 and for this 25 you checked and the answer was 50. So 50 is smaller than 54. And also you calculate the standard deviation of the above data and it comes out to be 8 gram. Can you prove statistically at 95% confidence that the claim might be false? These types of questions are done by having a good understanding of confidence interval. This session is about confidence interval. Confidence interval, it's a range of values that is likely to contain the true population parameter. For example, it could be mean, it could be proportion, or it could be difference with a certain level of confidence. Confidence generally is expressed as 90%, 95%, or 99%. Your 95% is the most common one. So let's take a look at an example. Suppose you survey 100 students to find their average study time for each day and you find that your sample mean is 3.4 hours with a 95% confidence interval given by this number right here. So what do you mean by this statement? It means that we are 95% confidence that the true average study time for all students, in other words, for your population, lies between 3.1 and 3.7. This is the pictorial representation of this statement. Another way of saying this thing is that given the sample data, there is a 95% probability that the true mean would lie between 3.1 and 3.7. In other words, between this and these values. 95% CI confidence interval. It means that if we repeatedly sample from a population and calculate the CIs for each one of these samples, then about 95% of the CI, they are going to contain your true mean mu. So let's understand this through an example. Suppose that the population mean is mu and that we are trying to determine mu. So I take a sample 1 and I find a CI. Let's say it comes out to be 611. So let's do it over here. So this is my 611 for my sample 1. So this is my 6 right here, 6, and this one right here is 11. All right. Then I take a sample 2 and I find a CI, 713. So this is my 7 over here. Okay, and this is my 13 over here. All right. I do the same thing for sample 3. For sample 3, let's say my CI is 1, 8. So this is 1 and this is 8. And I keep doing this thing for all the other samples. And assuming, let's say your true population mean is 10, and you're trying to determine what your true population mean is, you don't know, but let's say it's 10. So what it means is this, that this number 10 is going to be present in 95% of these intervals, of this one, of this one, this one, this one, this one, this one. So if you check all these intervals, all these CIs, 95% of them are going to contain your true mean. That's what this statement means. The width of your CI, it tells how precise your estimate is. So if you have a narrow CI, let's say 2.5, this is more precise than a wider CI, let's say 230, 2 to 30. 2.5 basically means that your mean can be anywhere between 2 to 5. This one says that your mean can be anywhere between 2 to 30. So clearly, you are more certain over here and you are less certain over here. Formula for the mean. If your population standard deviation is known, this is the expression to find your confidence interval. Your x bar is your sample mean, your z is the z value corresponding to your confidence level. It's going to be 1.96 if you're working with 95% confidence level, and it is going to be 2.58 if you're working with 99% confidence level. Your sigma is your population standard deviation, and n is your sample size. This term right here, which is same as this term, it has a special name. It's called margin of error, also known as maximum error of the estimate. Your estimate in this case is mean because that's what we are trying to estimate. Another way of writing this above expression, which is this right here, is use this right here. So in this case, I'm saying that my population mean, Okay, this mu is your population mean. The population mean is between this and this expression. This is your ME. So you can also rewrite the same expression like this. Your mu is between x bar minus ME and x bar plus ME. Your x bar is your sample mean. Two main assumptions apply over here when you're trying to find a confidence interval for the mean when your sigma is known. The first assumption is that the sample is a random sample. The other assumption is this: either your n is greater than 30, your sample size is more than 30, or your population is normally distributed when your n is less than 30. Now, formula for the mean. Previously, we used z distribution because population standard deviation was known to us. If your population standard deviation is not known, then we use t distribution. The degree of freedom is defined as n minus 1. You need this when you're using t distribution. We used df, which is degree of freedom, and confidence level to find the t values from the t distribution table. Your marginal error is defined similarly as you defined for your z distribution. Your z now is replaced by t and your sigma is replaced by s. All right. Your confidence interval is defined similarly. Before we use z, now we use t. Before we use sigma, now we use s over here. That's the only difference. If you look at the previous expression for my z distribution, I was using, let me remove everything, and I was using this expression right here. And now with t distribution, I'll be using this expression. So the only difference is my z is replaced by t and my sigma is replaced by s over here. So how do we decide when to use z distribution or t distribution? We start by asking ourselves this question: do we know sigma, the population standard deviation? Do we know that? If the answer is yes, then use your z distribution and sigma in your formula. Use this one. If the answer is no, then use t distribution and s in your formula. S in this case, it refers to your sample standard deviation. If your n, your sample size is less than 30, the variable should be normally distributed. So these are the steps you follow when you compute confidence interval. Number one, first you decide which distribution to use. Is it z or is it t distribution? And then you find their corresponding critical z value or t value. Second step, you compute the margin of error. If you're using z distribution, use this one. If you're using t distribution, use this expression right here. Step 3, construct the confidence interval. If you're using z distribution, you use these expression right here. If you're using t distribution, you use this expression right here. So this is a cheat sheet for z distribution, their common confidence level, their z values, and their meaning. If your confidence level is 90%, your z value is going to be 1.645. What it means is this: that you're 90% confident that your true mean would lie in that interval. In other words, it's going to be a narrow interval. So as you can see, this is going to be my interval. Let's say this is my interval for 90% confidence level. For 95%, which is this is the most common one, your z value is going to be 1.96, and this one is the most commonly used. So this would be your 95% confidence interval from here to here. And then you have 99% confidence level. In this case, your z value is going to be 2.58. In this case, you will have a very high confidence, and it comes at a price, and the price is that your interval is going to be very wide. So this is your 99% confidence level right here, from here all the way up to here. Problem: a factory wants to find the average weight mu of a packaged product. You take a random sample of 100 packages and you find the sample mean to be 50 gram. The population standard deviation is known to be as 8 gram. Find a 95% confidence interval for the true mean weight. So what's given to us? We know our sample size. I know my sample mean value is 50, and I know my population standard deviation is 8 gram, and I also know my confidence level, which is 95%. Step 1, since we know our population standard deviation, we are going to use z distribution. Here, I'm just following these steps right here, the steps I just explained to you a minute ago. My critical Z value for 95% confidence level comes out to be 1.96. I'm just looking at this cheat sheet right here. Okay, from here, I got my 1.96. All right, then compute your margin of error using this expression that I showed you a minute ago. This right here, compute your margin of error, and the answer comes out to be 1.568. I'll just substitute the value of Z, which is 1.96, substitute the value of sigma, which is 8, and under root n, which is the under root of size of your sample, which is under root 100. Then you construct your confidence interval. And my answer comes out to be mu is between 48.43 to 51.568. So in other words, we can say this, that we are 95% confident that the true mean weight of the packaged product, it lies between 48.43 gram and 51.57 gram, meaning that the procedure used to create this interval, this will capture the true mean in about 95% of the repeated random samples of size 100. So let's do previous problem, but with a smaller sample size, 49. So everything is same. I'm trying to, a factory wants to find the average weight of a packaged product. It takes a random sample of 49 packages, and the sample mean is 50 gram. The population standard deviation is known to be as 8 gram. Everything is same as the previous question, okay, except now I'm just taking a smaller number. So in this case, given to me, your n is 25, your sample mean is 50, and your standard deviation is 8 gram. Confidence level 95%. Follow the same steps. One, since we know our population standard deviation, we are going to use z distribution. So my z in this case comes out to be 1.96. Step two, compute your margin of error. Substitute your value sigma, your z, your sigma, and your n, and the answer comes out to be 2.24. So you notice something over here, your ME, your margin of error, became larger now. Previously, a margin of error was 1.568. Now your margin of error has become 2.24 because your sample size has become smaller. Now you construct your confidence interval. So I construct my confidence interval, and it comes out to be that your mu is between 47.76 and 52.24. In other words, we are 95% confident that the true mean weight of the packaged product lies between 47.76 gram and 52.24 gram. So for n equal to 100, when your sample size was 100, your confident interval was these numbers. For n equal to 49, when your sample size is 49, your confident interval was this number. And as you can see, that your sample size decreases. As your sample size decreases, the interval becomes wider. So the estimate is less precise. So let's do previous problem, but with a smaller sample size, n equal to 25 in this case. So a factory wants to find average weight of the packaged product. You take a random sample of 25 packages and you find the sample mean to be 50 gram. This sample standard deviation was calculated to be 8 gram. Okay. Find a 95% confidence interval for the true mean weight. So I know my n, 25. I know my mean, sample mean is 50 gram, and I know my sample standard deviation is 8 gram. My confidence level is 95%. Step one, since we already know our sample standard deviation S, we would use t distribution. Here, my degree of freedom is given by n minus 1. N is my sample size. It's going to be 25 minus 1 equal to 24. So using your t table, we find the critical t value to be t equal to 2.064. Step two, compute your margin of error, ME. This is the expression I'm using. And I got this, I showed you a minute ago that your expression for your margin of error would be this for your t distribution. All right. And I substitute my value of t, substitute your value of s, substitute your value of n. And the answer comes out to be 3.3024. Notice that your margin of error became larger now, which makes sense. If you remember, the last one was 2.24. Margin of error was 2.24 for the sample size 49. Now, when your sample size has gone down 25, your error actually increases. Your margin of error becomes bigger, which makes sense because if you're taking a smaller sample size, you are likely to make more mistake. Your error chance of making error goes up. So construct your confidence interval. I use my formula, which is this right here. I'm using this formula right here to construct my margin of my confidence interval. And this is my answer right here. So we are 95% confident that the true mean weight of the packaged product lies between 46.7 gram and 53.30 gram. So why do we need confidence interval? Number one, your point estimates alone are not complete. For example, a sample mean, for example, 3.5 hours, does not tell you how accurate this sample mean is. A confidence interval, it gives you range that quantifies the uncertainty. Number two, it accounts for sampling variability. Every sample will give you a slightly different result. What CI does, it shows you how much variation to expect. Number three, it helps in decision making. For example, let's say a new medication, a 95% CI for improvement is this number right here, okay, between 1.2 to 2.8. And this number does not have, this range does not include zero. So we can actually infer, we can conclude that the drug likely has a real effect because it does not have the zero in it. Number four, it is interpretable in real world terms. It's easier to explain uncertainty than p values.